Okay, folks, we were starting. Thanks a lot for joining us today. Okay, cool. Yeah, basically, welcome to the semester. Welcome to the class of linear system theory. I'm super excited to start teaching this class. It's my first class here at the University of Hawaii. I think it's gonna be more like a discussion about this like important math of control theory and linear systems. We are quite a small class, so please feel free to ask questions, interrupt me at any points. Today we are going through some logistics and some like introductory topics, and I expect to start actual math next time on Wednesday. So regarding the course logistics, there's first of all there's the very important website, Igor Molibog dot github.io, where there is a page E 650 fall 2023 HTML, where you can look up the important resources. So let me go to that website right now and show you everything. It's going to be there. So first of all, there is the course syllabus that explains the topics that we're going to be all going over week after week. There is a textbook. It's actually like lecture notes that were written by a person that I know very well during our studies back at Berkeley, and I will be following that, like those lecture notes, quite closely. So feel free to use them as our lecture notes. But I will also be making some notes myself, and I will share them as well. I hope to post the recordings on YouTube for those of you who like cannot make it for whatever reason. I don't promise that it will always work fine, so I would suggest to come here whenever it's possible. How the homeworks is going to be done is according to the following. There is a Google form, the submission Google form, where you would need to just upload your like a file with the homework that you have completed. The first problem set is already released. It's due in about a month. It will contain some tasks on linear algebra, very basic stuff. There is also a very important feedback form in case you don't want to share with me and you want to share like privately. You can just submit it there, and I'll make sure to incorporate that into class. There's also a number of recorded lectures that are going to be very useful that were taught in Berkeley several years ago. I found them very useful, and I will be following closely with that course. So whenever there is an additional material needed, you can consult with those lectures as well. This is regarding the website and the overall logistics. There will be 4 problem sets, and they are quite big themselves, but there are only four of them, and the deadlines are strict. So make sure that you follow them. Any questions? Cool. In that case, we can proceed to some introductions. We are a small class, and I will ask everyone here to introduce themselves, which is scary, but I think everyone needs to have some time to talk today. I will ask everyone to about who they are, why you guys are taking this class. For example, you want to learn math, or you need it for some other job that you like want to have when you graduated, or you already like have something that where you can apply this knowledge. What are the expectations of this class? Is it get some practical skills or improve your theory knowledge, or is it just like a GPA booster or something like that? I will start myself. So my name is Igor. I graduated from Berkeley a couple of years ago. I've been working at industry, basically training different versions of ChatGPT, like the large language models. I'm specializing in numerical optimization and control. This is my research area. Why am I teaching this class? Is because I love math myself, and I want to share that with others. I want there to be more people who enjoy it as much as I do. I hope that I can help you with that, basically. And I want to deepen my own understanding of this subject, and I would love to do that through teaching. Basically, that would definitely improve my knowledge. What are my expectations of this class? Is I hope to find the audience and the students who I can really discuss the advanced topics in math and in linear algebra and control theory, and who can potentially who I would be able to collaborate with. Now I have a list of students who are registered, but I think that some of them are not actually. So if it's possible to start from the right and go to the left and introduce yourself, guys, and answer the same questions.
I'm not registered. Just here for fun, and just here. My name is Chris. But only experience I really have with the linear system is a little bit model, and I did mostly what I want to do is actually try to understand a lot of the math a lot more. I think it's great for research, so I really want to try to really understand a lot of the that's what I can get out of class. And using the circuit designer, and I'm looking at those developers that are important. More invested.
Thanks. So theory also is something that you're interested in? Sounds good.
My name is Pona, but you can call me Kate. I am from Thailand. I studied fashion, and then I skipped my study PhD and master's degree. I work with other organizations. We are doing data measuring and visual. And I registered this, and I hope I get a good grade. Thank you. We will be tied to us.
Absolutely.
I'm Nick. I work with Dr. Rose Johnson at the Wetland. We look at information theory, transmitters. I took this class too, so I just get more.
You go ahead. Yes.
I get an college. I work at Pleasant, Michigan. Thoughts because easy group. I won't go, but I'm feeling now the truth.
Cool.
Actually my first semester back to school because I spent a year after I graduated working. Yeah, why not? I don't like it too much, so I'm back here. And undergrad, I like 351 a lot, so I'm here to hopefully have some fun. So.
Awesome.
Yeah, they like to fire people very much.
Cool. Well, great to meet you guys, everyone. I hope so. I just want to stress that collaboration is likely going to be very important within this class. It's not an easy class as for me, and I strongly encourage like cooperation during like homework assignments preparation. Although I expect everyone to submit their own files, but generally speaking, like you are very welcome to form study groups, refer to them within the homework assignments, and I hope that we can have a collaborative environment within this class. Also, don't hesitate to ping me for whatever reasons. Like if you are not able to find someone to study with, I think I might be able to help with that. So yeah, this is all great. From this point on, I think I should switch to the introduction to the actual class that we are going to be talking here about. Yes, that's a great question. The office hours are by appointment. I will be, or like after class, basically. Like, if you have questions after every class, we can just sit and go through all of them. Because like I'll be here anyways, and it's easier to catch me here rather than somewhere else. I have to say that sometimes I might have to travel, and I might actually have the class held remotely. In that case, we can just arrange an appointment regarding office hours. Does that sound good? Cool. Okay. So linear systems theory. Let's start with the systems part. Generally speaking, a system is a compound object or composite object. We normally distinguish between a stationary and a dynamical system. For now, let's keep it simple and say that it's just a composite object. No time for now. What is interesting about a system is a notion of like what comes with the notion of a system is a notion of state. State is basically a set of properties that are definitive for a particular system. We will be considering dynamical systems, which are actually evolving in time. Basically, it means that there's also a notion of time, such that like which is a real parameter of that the state depends on. And the evolution, you can think about the dynamical system as a state plus the time dimension, basically, that is evolving over time. The next critical notion within the class is the notion of a model, which is a simplified description or representation of a system. We are gonna be like, basically the phrase linear system doesn't really mean too much, because the actual linearity comes with the model of the system as a simplified representation. So within the class, we are gonna be talking primarily about the models that are linear, which we're gonna define slightly later today. Generally speaking, when we are talking about people who are studying systems and models, there are like two big clubs of professionals here. First of all, the scientists and the engineers. Theoretically speaking, like how I prefer to separate them, split them, is scientists are those people who are describing systems, and engineers are people who are building systems or controlling systems. Basically, having some. Basically, it's a difference between observing and changing something proactively changing. Obviously, research normally, like as you probably know, consists of like 4 steps. It's observation, right? Observation, meaning observation of a system. It is a hypothesis that comes up out of an observation. It's an experiment, or designing the experiment. And like basically coming back to the observation. So it is a kind of a closed loop. And here we can see that one of the arrows here corresponds strictly to the engineering part, or basically modeling, or given a physical or something real, such as a system, we need to construct something that is abstract, which is a hypothesis based on some simplified representation of the system, which is the model. So the engineering falls here, and the science falls here. This is an abstract separational split between the folks who are working on modeling in general, which is not yeah. Let's come to a more concrete example. Let's take as a system the Hubble Space Telescope, for example. Hubble Space Telescope can be modeled in several different ways. First of all, it is a space object, which means that one of the appropriate models for it would be a material point that is being launched into the space with a rocket. So first, the first models is just a material point. Another model that is also could be applicable here is a model of a rigid body, because like Hubble, like the space telescope, it is a like an object. It has a its own geometry. It has momentum, and probably for the purpose of positioning it correctly, it would be more applicable to consider the rigid the telescope as a rigid body. Another like a totally separately different model would be a model of a telescope that has properties such as aperture, or generally speaking, like optical or electromagnetic theory involved into modeling of this telescope, which is basically like a telescope. Let's say it's the telescope model. We can see that a single system can be modeled in a few different ways depending on the applications for which the modeling is done, and how basically how to tell which option is better in one way or another, in one case or another. For example, if we want to change the altitude of the telescope from one to a different one, which one of this models would be more applicable? Telescope model. Any other versions? We want to change the altitude of the telescope. A point, material point. Okay. And any other versions? There's only one left. Yeah, I would think that probably modeling as a material point would be a more applicable version of this in this scenario. It might be not totally clear at this point, but actually, how do we compare a model between one another? Well, the utility of a model is in its predictive power. So depending on how exact the predictions of a model would be, we can say that the model is more applicable or less applicable. So basically, the choice. Okay, let me actually write it down. So utility of a model is its predictive power. Okay. So from this kind of abstract definitions of a model and a system and a state, we can come up with a definition of a dynamical system. So a dynamical system is a system plus time, where a system is normally represented with a model that has a specific state described with a state, and time is normally a parameter, real value parameter. There are several ways to categorize what is a dynamical system, and they are based on top of the notions of state and time. First way, the first way to categorize, so categorization. of a dynamical system. First of all, there is a category of like depending on the state. It's either discrete or it is continuous. The same with the time. It could be also discrete or continuous. In which case we would separately describe discrete state, continuous time, or discrete or continuous state, discrete time, or discrete state, discrete time systems. Let us come up with several examples. One would be, for example, let's consider where the like a case where the state space is discrete, and the time space is also discrete. They are like systems like this, discrete state, discrete time, are normally represented with a diagram where, like, let's say that the number of states is not it's, the state space is not only discrete, it's also finite. It consists of several states that we can like call S1, S2, S3. And there are like certain transitions that between the states that, like, for example, they're happening every time step. So from S1 we go to S2, from S2 we go to S3, and from S3 we go to S4. So this is a extremely simple example of a system. However, you can see that the explanation of this would not be possible without introducing a new notion, the notion of a transition. So whenever we are describing a dynamical system, ever since we have introduced time, there is a notion of a transition that is normally described with with a specific, like with a certain like function, for example, like certain mapping that takes as an input like an origin state and returns as an output target state. The notion of transition function is going to be crucial within this course, because basically the transition function is something that is going to be linear eventually. Okay, so coming back to our categorization, we can say that like we can map out what exactly are the types of systems that we're going to be studying within this course. So we have the dynamical systems, that are represented by mathematical models. There's a direct correspondence between them, but essentially a single system normally is being described by several models. And then mathematical models could be continuous time, they could be discrete time, and they could be Okay, so basically, okay, let me actually change this a little bit. So we are talking about continuous space here, because we are going to be talking about continuous space specifically, and there's also a discrete space or discrete state that is going to be outside of the scope of this specific course. When you have the continuous space systems, we can we're going to be discussing separately continuous time and discrete time, and in each of them we're going to be separating linear and nonlinear systems. Between linear and nonlinear systems, we also are going to be separating but basically within linear systems, we're going to be separating time variant and time invariant systems, and the same thing for the discrete time case. The notion of time variant and invariance is an important notion that is going to come up later within the course. Within this diagram, these parts are the parts that are going to be most important. Are the parts that we are going to be discussing during these lectures. This is going to be the focus of our course. The continuous space, continuous time systems are normally their transitions are normally described through the differential equations, and for continuous space discrete time systems, the transitions functions are normally described as difference equations. So within this course, we're going to be discussing the questions of so given a linear differential equation, what's the procedure, how can we predict the behavior of the system over time. And also, how can we control such system? Are there any questions here? Those are time variant and time invariant types of systems. We will get to that slightly later, but essentially, it is like the kinds of systems that are dependent or independent, the dynamics might be dependent or independent on the time. That's the main difference there. There are systems where, from a specific state, you will the transition is going to be predetermined independently on which place in time you are at. Those are time invariant systems, and there are systems where the transition is going to depend on the exact value of time, and those are going to be time variant. Okay. Any other questions? I know this is very kind of abstract and about nothing, right? Well, we'll get to math a bit later. I know you guys are very excited about this. So. Okay. Let us take a look at some basic examples where the linear, like basically linear modeling is applicable. Most of the like aircraft design, air traffic control, power engineering, basically even like right now in quantum chemistry and biological motor control and all of these spheres, there are systems that are being modeled, like basically in the first approximations, in the first approximation, any system can be modeled as a linear one. There is a separate kind of group of systems that are not being modeled at all, like not being, at least not being analytically modeled. And I would like to point them out right now, which are like basically the realm of machine learning modeling and automatic, like basically automatic modeling from data. This is some like a different types of models that we are not going to be discussed. We're not going to discuss directly within this course, but like obviously there is like a contrastive kind of approach to modeling, like to like do predictive modeling of systems that is less analytical and more automatic. That would it will prove useful slightly later in the course. I will try to tie the advances that we are having within like machine learning and like how can we actually use modeling systems that are like the automatic. How can we use these approaches to understand better the automatic modeling systems that we are using in practice? Basically, how can we model systems that are modeling other systems? And in this case, it is possible to apply the apparatus that we're going to be developing within this course. Okay, so coming closer to the like what exactly is like how is modeling being done in practice? There are several very important steps in which like which are called the steps in modeling. The first step is the verification. Let's say that you have two models of a system, model 1 and model 2. They like basically the system here is a black box. That takes something as an input and produces a certain a specific output depending on its state. We have two models of the system, and let's say that model 1 is a simpler one and model 2 is a more difficult one. Basically, it means that for model 1 we can like simpler for analytical operations. For example, given a desired output of the system, the model 1 can like we can use model 1 in order to design a specific input that we would expect the like to be fed into the model in order to receive like a particular outcome. For model 2, let's say that we cannot use it in order to use like okay. So let me introduce the notion of control. Notion of control is the problem of designing input given a desired output of a system. So how can we design an input? So it's an inverse problem to the modeling problem. The modeling problem would be given an input, can we predict an output of a specific system? When we're talking about control, it is mostly about the inverse of this. So given an output, can we say which input we need to give into the systems to produce the desired output? And let's say that model 1 is simpler for that specific purpose. So model 1 is simpler from the control viewpoint than model 2, but both of them are kind of good models, and they have like have some predictive power. How can we use both of these models in order to understand better if whatever input we have designed is like whatever controller we have came up with is a good controller? The process of verification tells us that what we should do is we should control based on model 1 and evaluate based on model 2. Essentially, this is an extremely useful technique because normally the model 1 is the linear model, and the model 2 is something that you come up with that has potentially more like a better predictive power, but something that is intractable to solve during from the viewpoint of inversion. And you can tweak the way that you do linearization, the way that basically how exactly you linearize your system. You can change those decision variables, decision parameters based on the process of verification. Besides, are there any questions regarding verifications? Simple concept. The next kind of another approach how a model can be evaluated is based on a simulation. The concept is similar, but in this case we have just one model that we have used in order to design and output. We use it in order to design a controller. That essentially is supposed to provide us output input pairs. And then we can feed the inputs that the controller is spitting out to a simulator of a system, which is simulator by itself is normally also a kind of a model, but it's normally just a numerical model that can provide us a simulated output of a system that the system would have given to us if we were to just feed the input into it. And also we can compare model output to the simulate output. And again, refine and develop on top of this knowledge. And lastly, normally the most expensive way to evaluate the model is the validation. Basically, feed the so essentially we have the model. We design controller on top of that, and we have an example of a system, and we feed the control input in order to observe. An output. In after that, we again can compare it to the outputs that our model would be predicting, and refine our model on top of based on this comparison. Okay, are there any questions about the introduction, about the models that we are going to be discussing, and generally speaking, the scope of the course? No questions? This is awesome. Okay, in that case, we can actually proceed to the interesting parts where we discuss the basic definitions of linear algebra, and see if there are any new concepts that we can encounter here. So what's gonna come next is the definitions and the basic properties. Okay, let me probably separate this. Definition and basic properties of different linear algebra notions. Okay. There's a bunch of interesting references that are listed in the lecture notes, and I will post some on the website as well. So whenever you need to consult with anything, you can use those resources as well. So first of all, the notation, right? So we're gonna introduce the notation for the sets of numbers, the natural numbers, the integers, rational numbers, real numbers, and complex numbers. We're gonna use quantifiers such as belongs, does not belong, for all, exists, exists unique, and so forth. There is also signs such as implication, one way, the other way, and the equivalence relationship. Are there any questions about the notation? Does everyone? Okay, it's familiar for the majority. Sounds good. The definition, the basic definitions that we're going to be introducing, the first one is the Cartesian product. Given two sets, X and Y, a Cartesian product is going to be denoted as X, Y, and it is the set of all pairs X from X and Y from Y, or another way, like formally we can write down XY is the set of pairs XY where X belongs to X, Y belongs to Y. Next definition is the definition of a function. Yeah? No. So basically, you can think about it as, for example, let me put down. That's a good question, by the way. Thanks for asking. The example would be a Cartesian product of like an interval 0, 1 with itself. Can anyone say what like how can we represent that? How can we like draw this Cartesian product? Can you speak up? Right. So since we are here we are talking about intervals that are infinite. We're gonna be we can represent it as a square essentially. So let's position our first interval between 0 and 1 vertically. The other one is gonna be horizontal, 0, 1, and the entire square is going to be the Cartesian product. So it will contain any kind of pair of x, y, where x is going to be coming from this interval and y is going to be coming from this interval. Any pair is going to be part of our Cartesian product, right? If you want to have like a totally different sets, another example. We can have like two sets that are discrete. Let's say that the first set is going to be a set of letters A, B, C, and the second set is going to be this like a set of numbers, say 1 and 2, and the Cartesian product is going to be the set equal A1, A2, B1, B2, C1, C2. Okay. Any questions here? Duplicates the pair cannot be duplicated itself. But a single entry from one of the sets will almost certainly be duplicated. For example, A can be met here and here in both of these points. Good question. Okay. The next definition is the definition of a function. Given two sets, X and Y, a a function from x to y is a mapping that assigns a unique value of f of x from y to every x from x. And we say that also we like denote that f of x, the capital X, is the set of all f of small x for all x from the capital X. The key part in this definition is the word unique. This is something that is important to remember, because it's not just any mapping, but a mapping into a unique value from y. If we have, let's say that we have a mapping. Okay, are there any questions here? No questions? No questions? No questions for sure. Okay, so the question of mine is the following. Let's say that we have let's say that we have a mapping mapping f from x to y that, let's say, maps x0 that belongs to x. It maps, so f of x0 equals to y0 and y1. Basically, it maps a single point into two different points. Is this mapping a function? It's not. Cool. Is there any way that we can redefine our sets of, so the set X is called domain here, and set Y is called basically a pre-image, or like pre-image. Is there any way we can redefine the domain and pre-image to change the mapping into a function? Small domain is one thing. Yeah, good point. Good point. Right. Yeah. Precisely. We can modify the domain in order to exclude x0. We can also modify the pre-image to include there another point that is y0, y1, like a pair. It's gonna be like a new pre-image is gonna be y union with something like that, 0, 1, y0, y1, and in this case, f from x to y bar is going to be a function. Okay. Any questions here? Okay, so I think the more common like notion for pre-image is actually is codomain. But image is also a thing. Basically, the set of all. So let me make another definition. Image of a function from x to y is a set of all y's in y such that exists x from capital X, such that f of x is equal to y. Essentially, it is image. It's a set of all elements of the codomain such that it has an x. There is an argument such that this particular specific function maps the argument into the image. Are there any questions here? The image itself is not a mapping. It is a subset. An inverse would be a mapping from the codomain into domain. But here we would not describe a mapping at all. It's a subset. You can let's put an image into our head. So let's say that we have x and we have y, and we map every point from x into a specific point y. X we map into y, and then we map the entire x into some part of the image y. First of all, all axes have to be mapped. First of all, and but like not every y has to be mapped into, right? So basically, this smaller subset is called the image of f. Does that make any sense? Yes. Yes. Great. Next point is the injective function. A function f from x to y is called injective or one-to-one if for any x1, x2 in from the domain x, f of x1 equals to f of x2 is equivalent to saying that x1 equals to x2. It basically means that if you basically that there is only one, there's only one y that an x way. So let me put it this way. Two different x's cannot be mapped into the same image y. That's basically, let me also draw it from probably. So this is x, this is y. We have two different points, x1, x2. They have to map into different y1, y2, and a situation where they both are being mapped into the same y0 is prohibited. So this is prohibited. Does that make sense? Any questions? Okay. A surjective function. let me actually let me add some properties. Anyway, you can read about the additional properties in the textbook. I don't want to stop on that. So a function f from x to y is surjective if for each y in capital Y there exists x in capital X such that y equals to f of x. We can we can draw this in the following way. Let's say that we have our x and we have our y. It means that x's are covering y, and essentially it means that basically it means that y, in other words, y equals to the image of f. Basically, it means that for every y in the capital Y set, there exists an x such that x maps into y. Any questions? Yes. So you can have for like oh, great question. Okay. So you're basically saying that this situation is also possible when we have x that is here and we have y that is smaller, and we are mapping this like subset of x into y. By the definition of a function, every single point from the capital X set has to be mapped into y. So while it might be true that even if you have a reduction of your function onto a specific subset and that covers y, that would be a sufficient condition for the function to be surjective, but not a necessary one. Good question. Here, like, we use the notion of a reduction of a function to a specific subset. Should I define that formally? Should I? Okay. Okay. Let me give an example, and then I'll define a reduction. So let's say that we have once again the set of A, B, C, and we have another set which is X, and our other set Y is 1 and 2. 1 and 2. Can someone give me an example of a function that is surjective? Cool. Okay. So A being mapped into 1, B being mapped into 2, C being mapped into 1. Yes, that is correct. We can take any value on the right hand side, or like from our Y set, either 1 or 2, and for each of them we would be able to find an argument that is being that the function is mapping into our image. For example, if we take 1, there are actually 2 arguments. Our argument is going to be A, and our argument might be actually C as well. If we take 2, then our argument would be B. So this is a proof that our function f that was proposed is in fact a surjective one. Is this an injective function too? It's not. Why? Exactly. We have a value of 1 within our y set, such that there exists two points in our x set that are being mapped into this same value. Which contradicts the definition of injectivity. Any questions? It's all clear, or is there something that I have already missed? No questions. Cool. Then let me quickly define what is the restriction. Let's say that of f. Let's say that f is from x to y, and we have some subset x 0 that is a subset of x, a strict subset. A restriction is f restricted onto x0, such which is a function from x0 to y, such that for all x from x0, f of x equals to f, the value of the restriction x0 of x. Basically, this is a function with a restricted domain. Okay, probably the last definition for today would be the bijective function. Bijective function or bijection is a function from x to y, such that it's both injective and surjective as well. In other words, for any y, actually it should be a theorem, should not be. So like basically this is the definition, and now that there's a proposition that is saying that f is bijective if and only if. This is how I'm going to be stating the equivalence relationship, right? So this is if and only if is the same as saying that the statements are equivalent. For any y from the capital Y set, there exists unique x from our domain such that y equals to f of x. In other words, for like basically we have an exact correspondence between our two sets, x and y. For every x, there's always a unique y that x is being mapped into, and for every y, there is a unique x that is being mapped into y. This is a proposition. It would need to be proven from the definition. We can either do it like in class, probably like next time, if you guys are interested. Otherwise, it is a very good exercise to prepare for the next lecture. Basically, would be left as an exercise. Awesome. I think we are done for today, guys. Next time we will continue introducing new notions, and we'll start forming some better understanding of where we will go with them. Thank you very much for your attention. If you have questions, yes, please. Where exactly are you reading?
Wasn't that like
Say it again.
symbolism?
This ones that I introduced in the very beginning. This ones. This ones. The last one is exists unique. Yes. Yes.
So about this one, so the property of the model one is it's like a linear model. So I wonder what should be like properties of the model two in terms of.
It should have better predictive power. Basically, it should have other properties from the prediction of the output of the system. It should be closer to the actual output of the system. Thank you.